Okay, welcome to energy. Just a quick review of work. Work is a change in energy, and the total work done is equal to the net force times the distance traveled. You know this. It's not that surprising, so I'm going to move on. Translational kinetic energy. It's called translational because it moves the object. It does not rotate the object. And so translational kinetic energy is the type we're going to look at. So it is the kind of energy that moves the object. So it's a force that's acting through the center of gravity on the object. Now, kinetic energy. Here we go. This should be familiar. I'm doing a different color here. K is equal to 1/2 mv squared, which, at this point you got to know what that is. It is the energy of motion. Energy of motion. And you got two things. The greater the mass, the greater the kinetic energy. But here's the other thing, that a change in velocity gives you a much bigger change in the kinetic energy because of that velocity squared. So for example, if I have 2 times the velocity, that leads to 4 times the kinetic energy, because 2 squared equals 4. This is not new. You know this. I just want to remind you, because thinking about proportionality is going to be one of those things that helps you with the multiple choice questions. So if I double my speed, I get 4 times the energy. If I cut my speed in half, I get 4 times less energy. That's a multiple choice thing that you need to know. Okay, gravitational potential. The book splits things up into 2 types of gravitational potential, and it'll make sense once that I've explained it. The most common that we work with is when the force of gravity is constant, in other words, somewhere near the surface of the Earth. This is the kind of gravitational potential energy that we had last year. Now, here's the thing. The letter U represents gravitational potential energy. And I wish I could tell you why it's U. I should probably look it up and let you guys know, but in the end, the letter U represents gravitational potential energy. Now, U grav is equal to mgy. Why, you might ask? Assuming that y is up and down. Okay, so we're using the letter y to represent the height, so mgy. Of course, g is constant near the surface, and y is your displacement. From some zero. And of course, as you know, that zero is kind of arbitrary. Usually we use the surface or the ground, but it may be convenient to use like a tabletop or something else as our zero, because if you're looking at the change in potential energy, you can set up the coordinate system any way that's convenient. So, gravitational potential near the surface of the Earth is mgy. Y is, of course, the vertical displacement. Okay. Gravitational potential energy when the force of gravity is not constant, in other words, out in space. Now, if you remember correctly, Newton's law of universal gravity says F is equal to big G m1 m2 over r squared. And I think the book puts a minus in there. And here's the thing, negative forces attract. That's something we don't really emphasize a whole lot, but negative forces are attractive forces. They pull things together. So this is often written with a negative sign. Okay, so this is the law of universal gravity. Now, if you remember, work is equal to the net force times the distance. Well, in this case, delta x is r, the distance between example, the Earth and the Sun, or the Earth and the Moon, or some satellite in orbit around the Earth. So in that case, if we take this force times the distance, so if we do this, negative g m1 m2 over r squared times r, we lose an r there, and so u is equal to negative g m1 m2 over r, not r squared, for reasons I just explained. Okay, so universal gravity out in space, in other words, when the force of gravity depends on the distance between the objects, is this. U equals negative g m1 m2 over r, not r squared. All right, let's do an example. Okay. This is basically taken from page 204 in the book. I added a few numbers to make the equation or the calculation more straightforward. So how much does gravitational potential between the Sun and Mercury change as it orbits? So the distance between the Sun and Mercury at its closest point is 4.6 e10 meters. The distance at the farthest point is almost 7 times 10 to the 10 meters. Of course, the mass of Mercury, 3.3 times 10 to the 23 kilograms. Mass of the Sun, 1.99 times 10 to the 30 kilograms. Those are just numbers that, I don't expect you to memorize those numbers. I just looked them up and I wrote them down so that it was convenient for the problem. All right, so in the end, what you do is U is equal to negative G M1 M2 over R. So I have negative 6.67 times 10 to the negative 11 times 3.3 E23 times 1.99 E30, all that over 4.6 E10. That is the potential at the nearest point. And that ends up being, let me just check my notes, it ends up being, let's see, 6.27 times 10 to the 32, well, energies in joules. I'm going to scroll down here a little bit. All right, so U far is going to be the same numbers up here divided by 6.98 E10, and that ends up giving you 9.52 times 10 to the 32 joules. Now, take a look at this for a minute. I mean, you should be able to do the subtraction without too much trouble. 9.52 minus 6.27 is still 10 to the 32 joules. That's a huge amount of energy. And if you look at the example in the book, orbital speed of Mercury, this change in potential energy translates to a change of 20,000 meters per second. So when Mercury is at its closest point, it's going 20,000 meters per second faster than at its farthest point. That's pretty significant, and that's one of the advantages of being able to calculate the force, the gravitational potential for objects out in space. Thanks. That's it for potential and kinetic energy.